Alright, ladies and gentlemen, my goal with this video is actually to go through the entire Unit 3, Uniform Circular Motion and Gravitation. It is a shorter unit, as you probably already realized, since we are going to be testing here in just a couple days, and it's only been about 2 weeks since we started this unit, so we are really cruising right along through it. So my goal is to get everything into this video, some practice problems, just reminders of some of the concepts that you need for the test. But at the same time, I realize that many of you won't need every single piece of this, so down in the description I've got some sort of timestamps, so if you're looking for a particular type of problem or help with a particular idea, those will be sort of labeled out for you in the bottom, so you can just skip to whatever part in the video that sort of corresponds to. So I would imagine you probably wouldn't watch the entire video unless you want to, and then that's great too. So uniform circular motion is motion in a circle of constant radius and constant speed. Constant radius just means that it is in fact a circle, but constant speed is what makes it uniform. That's the more important part. We're not getting faster or slower through the circle, and UCM, uniform circular motion, is still accelerated motion. Question might say, alright, an object is moving around a turn at a constant speed. What is the acceleration of the object? And 0 will likely be one of your choices to pick, but that is wrong. Just because we're not speeding up or slowing down, we can still be accelerating because we are turning. So we're making a couple edits to some of the equations or variables that we've had in the past. Acceleration now, instead of being delta v over delta t, the change in velocity over change in time, it's now going to be v squared over r. You do not need to know how to derive that or anything like that. Just accept it the way it is. It's on your green sheet to help you as well. That is a centripetal acceleration, and it is always directed into the center of a circular path. The center of a circular path. So as we go around a circle, sort of arrow, the vector for acceleration, always points towards the middle at every single point around that circle. It is still acceleration, so it is still meters per second squared, but this time it's not speeding up or slowing down, we're just turning the entire time. And because we're working with forces, accelerations, and masses, we can still use net force equals ma, but this time our a is going to get substituted in to be net force equals mv squared over r. That is the net force along a circular path, and again, it is always directed towards the center of a circular path. So the only forces we are really going to worry about in this unit are ones that point directly into or directly out of a circle. We're not worried about any that are sort of at an angle per se. We're more worried about the ones that cause that circular motion, the one that's pointed into or out of the circle. So here we just have a little illustration. I guess there's a smiley face there because I forgot to clear off the notes page from whenever we did this in class. But a couple things about motion in a circle. Again, just like before, we still have our acceleration and the net force pointed towards the middle of the circle in each position. No matter what position you pick, it could be here, it could be here, it could be here. It doesn't matter. All of those accelerations and net forces for that position point towards the center of the circle, whatever sort of direction that is. That's the direction it points. And our velocity is always a tangent to that point and to the circle. The velocity is not at all towards or away from the circle. It is a direct line that is perpendicular to that acceleration and perpendicular to that net force. Whether it's up or down, for instance on this point, is dependent on what direction our object is traveling. In this case it says that it is clockwise, which means that's going to point up on the left and down on the right. It's pointing sort of in the direction of that motion. It's going clockwise, so it's pointing in the direction that would keep it going clockwise. In order to work with these, a lot of times it's not just going to give you the velocity or give you sort of variables that would be really nice to have. Instead, it's going to give you the time that it takes to go around a circle and the distance, the radius of that circle. So we need to be able to get from there to our speed, to our velocity, and we're going to do that by using what's called the period. It's represented as a capital T. Be careful because we also do use T's as tension. So just as you're writing these, be careful, make sure you know which T that you are referring to, because there will be problems that involve, you know, the period of the circle as well as the tension. It could be, you know, a tension-related problem that incorporates both of these, so it's easy to get mixed up there. The period is just the amount of time it takes an object to make one circular path. Its units are in seconds, and we're going to largely use the period as our time when we determine our speed or our velocity. Occasionally, a problem might say give you the frequency, represented with a lowercase f, and this is the number of cycles that an object makes per second. This is the inverse of the period, whereas the period is 1 over f, the frequency is 1 over t, 1 over that period. Frequency is represented as the per second, or second to the negative first, or the hertz, or hertz. We will use this a lot more later on in the year. It's not as applicable here. We prefer to use the period. The period is much more valuable. So if you are given a frequency, a number of cycles per second, just flip it over, put it 1 over that number, and that gets you the period. So because we're working in a circle, we need the distance around that circle and the time it takes to go around that circle. If we could do that, we can find our speed, which is distance over time. The distance is going to be 2 pi r. That's the circumference of a circle. I believe that should be on your green sheet, but if it's not, you should probably know 2 pi r as the circumference. So that's going to be our distance for all of these problems. And the period is the time it takes for one rotation. So we're saying that the distance of one rotation over the time for one rotation is our speed. And that is the speed or the velocity that we are going to use in that equation from before, that mv squared over r. And I apologize for my handwriting. I don't have my stylus, so I'm trying to just use my finger, which is not necessarily conducive to excellent handwriting. So I apologize for that right off the bat. Just a little refresh of all the equations that we've used so far and that we will use throughout this first half of the unit for uniform circular motion. The acceleration is v squared over r, and then the frequency and period. Velocity, a lot of times we'll use as 2 pi r over t, which can then get substituted in to that v if we're not just given the speed outright. If we're given the radius and the period instead, we can use that v to calculate our acceleration. And we also have Newton's second law, net force equals ma, but in this case that a is v squared over r. And don't let this sort of layout of the equation fool you. It's the exact same thing. It's still just net force equals ma. So here I want to start a couple problems with these, and these are going to be pretty basic to start, and then we'll work our way up into sort of more challenging ones. So the first one just has some object moving in what is mostly a circle, and let's say that our object is right about here. That's a terrible drawing. Let me see what I can do here. So let's say that our object is right in this spot. So at this spot, I'm going to say that it's exactly on that sort of edge on that left side. It's moving at a velocity of 4 meters per second, and the circle has a radius of 3 meters, and I want to know both my acceleration and my net force. So acceleration is just v squared over r, and my net force is going to be the mass times that acceleration. So also, let's just say that the mass is 4 kilograms. So to find my acceleration, I'm going to take 4 squared over 3. 16 over 3 is a little over 5. It's 5.33, I believe. And that is meters per second squared. So we just plug everything in here, all of our variables. This goes in there, and this goes in there, and we get our acceleration. So we take that acceleration and multiply it by the mass. So we get a net force. Erase that. Again, net force equals MA. Oh, there we go. Net force equals MA. We found our acceleration was that 5.33. And the mass of our object was 4. The acceleration, again, 5.33. And that is going to equal 21.3 newtons. So that force, that 21.3, is pointed directly into the center of our sphere, of our circle. And that is the net force. So it could be a combination of multiple forces. There could be one pointing outward and one pointing in, but when they add together, it has to end up being 21.3 newtons into the middle of the circle. Alright, for this next problem I want you to imagine that you are on a Ferris wheel. So this is sort of a side view of the Ferris wheel. And we're going to look at the Ferris wheel in 2 separate spots. The first is going to be the bottom. So forces acting on you when you are in a Ferris wheel, sort of on the ride, you would have your weight pulling down and the normal force pulling up. So these are both forces that we are going to be worried about. They go either directly into or directly out of the middle of the circle. On the side, if this box was on the side, neither of those forces would be ones we really needed to worry about. They would be there to accelerate us straight up and down, but neither of those go into or out of the circle. There are other forces that keep you moving around that circle as you go around the Ferris wheel. So let's say, for instance, that the Ferris wheel had a radius of 9 meters and it had a velocity of 6 meters per second. It's zooming along pretty good. And let's say that my mass is about 90 kilograms, which is true. And I want to know what the normal force acting on me when I'm at the bottom of the Ferris wheel is. So I'm going to set up my net force equals mv squared over r. Net force equals mv squared over r. And I'm just going to start plugging stuff in. I've got my normal force, and I've got my mg. M is 90 times 10 is going to give me 900. And that equals my mass, again, of 90 times v squared, 6 squared, over the radius, that 9. So I am getting, oh, that's moving very badly. Apologize for that. I'll work over here. So on the right side, I'm getting 90 times 36 divided by 9, which is the same as 10 times 36, so 360 equals normal force minus 900. So the normal force here is equal to 1260 newtons. You'll notice that this is larger than my weight. So if I was just standing still on a surface, any surface, I would have a normal force pushing up on me of 900. Because this 1260 is larger than that sort of normal force, the normal force, that means that I feel heavier than I normally would. I feel about a little less than 1.5 times heavier than normal. And I want to do the same thing at the top. I want to get my normal force acting up. The seat is pushing up on me. It's supposed to be an N. And my mg, again, is pointing down. This time my net force has to be, again, towards the center of the circle, but that is down instead of up. So this time I'm going to make my weight positive. That mg is going to be positive. I want anything that's towards the middle circle as the positive direction. So this time I've got 900 minus the normal force, and again that's going to equal the same stuff on the right side, so that equals 360. A little bit of math here, and we end up with 540 as my normal force. So now my normal force is less than my sort of everyday weight, which means that I feel lighter than normal. As you're at the top and sort of coming over the top of the Ferris wheel, you feel sort of a little bit weightless, not entirely, but you feel lighter than normal as you come over the top. This is exactly why. Your normal force, the force that the seat is having to push up on you with, is actually less than it would be if you were just standing on the ground. So you feel a little bit lighter. All right, the next problem I want to take a look at is one where a car is going around a turn. So we got a little turn, and we've got a poorly drawn car on it. But we have a couple of forces that act on our car. We've got the weight that pushes down straight into the ground, sort of into the screen from where you're sitting, as well as the normal force that's pointing out at you. But neither one of those are centripetal forces. They don't go towards the center of this turn. The only one that does is actually the force of friction that is caused by the tires in contact with the road. So in class we did a couple or sort of a example with that to determine the maximum speed sort of equation for a car going around a turn. We said that the maximum speed is going to be this with a bunch of variables. But this time I want to take a look at it with some actual numbers to give a little practice working with this type of problem. So I'm going to say that the radius of our turn's radius is going to be, we'll say it's a 10-meter radius for that turn. And the car is going with a speed of 45 meters per second. That's pretty fast, going around this turn of 10 meters. So what I want to know is what coefficient of friction would have to be present in order for this car to be able to do this turn at this speed. What's the minimum coefficient of static friction? Because this is static friction, the car is not sliding on its wheels. Sure, the wheels are rolling, but the wheels are not actually, the tires are not sliding against the ground. They're not skidding, and that would be kinetic friction. But this is static friction. So I want to know what that coefficient would have to be. And we have to pull a couple of different equations out first. The first is that at its maximum, the force of friction is equal to mu sub s times the normal force. So in order for the normal force, we are going to need the mass of the car, and I'm going to say that it is a 1,000 kilograms. That might be a lot. Maybe it's a big truck. I don't know. 1,000 kilograms for our mass. So this is the maximum force of static friction. This is the most that this force can be, and if we're looking for the minimum coefficient of static friction, we're looking for it where the friction is doing the most that it possibly can. So that is actually going to be our centripetal force. So I'm going to say that mu sub s times the normal force is equal to mv squared over r. So from here I can start putting in some variables. I'm sorry, some numbers. So mu sub s is what I'm looking for. My normal force is going to be that 1,000 times 10, and that is equal to 1,000 times my velocity squared. My velocity was 45. That's 45 squared over the radius, which I said I think was 10 meters. 10 meters in this case. So I can go ahead and do a couple of things here. I can say that These 1000s will cancel out because the mass ends up not mattering at all for these types of problems. The masses are on both sides, so they will just cancel out. And 45 squared is 2025. So 2025 over 10, and I'm also going to divide that 10 over, so really it's over 10 times 10. So mu sub s is equal to this number, which ends up being divided by 100, 2.02, which is massive. I cannot think of a single car or any sort of tire that could make this turn at this speed. 2.2 is an excessive mu sub s. That's sort of unheard of. So to try to take a turn going 45 meters per second around a turn that has a radius of 10 meters is highly unlikely. Just a reminder though, I'm going to sort of shift some of this stuff up into this big mess of nothingness. The equation to determine what the fastest speed that we could go around a turn is, if we had worked a lot of this with variables, we would have found that if we were just going to isolate that velocity, I'm going to kind of do it from actually this equation here. So if I just wanted my velocity by itself, I would say that is mu sub s times the normal force, which is mg, and then I would also multiply, not divide, that r to the other side. That would equal mv squared. These m's cancel out just like they did before. So I am left with the square root of mu sub s times g times r. That is the fastest speed. So this is the fastest I can go around a turn. Fast around a turn. Based on whatever that mu sub s is and whatever the radius is, that limits how fast I can go without slipping out of that circular motion. If my radius is bigger, that means I can go faster. The bigger your radius is, if you're getting on an on-ramp onto the highway, you tend to be able to go a lot faster than if you're trying to make a quick right turn onto a side street with a much lower radius. And the better your tires are, the higher that mu sub s is, the faster you can make a turn as well. My tires are pretty not good, so I tend to take it a little bit slower just for my own safety there. But this equation here will tell us how fast we can go around a turn at our maximum. The next problem we have is a loop-the-loop problem, or we also did this with a fighter pilot going around a circle, a loop. So I'll just do it as one of these circles here. Let me get a nice circle going for it. That is not a circle, that is a square. There we go. So if I got a circle, and the circle problems are sort of the opposite of the previous problems we did. With the previous ones, it was how fast is your maximum. But for these loop-the-loops, it's actually how slow is your minimum. You have to be going a certain speed at the top in order to be able to get around one of these circles. So at the bottom, just like sort of on the Ferris wheel problem, we've got the normal force pointing up. You know, the bottom of our seat is pushing up on us, and we have the mg, the weight pointing downwards. So that's the same as on that Ferris wheel, but this time on the top, the normal force is actually pushing our car down, and so is mg. So at the top, the ground, whatever that sort of ramp is made out of, in the case of the fighter pilot, it was the pilot's seat, pushed him downwards with mg. So in order for us to sort of make it around the top of the loop, we have to have a normal force that is as close to zero as possible. We want to just be in contact with that circle. So we want it so low that we actually make the normal force equal to 0, but just barely equal to 0. We don't want some sort of negative normal force coming into our calculations. We are looking for the speed that will get mg to get us around the circle without the need for any normal force, or as very little normal force as possible, which we just round to 0. So net force equals ma. And we would have mg plus the normal force, but again that is 0, so I'm just going to leave it out altogether. And that is going to equal the mass of my car times his velocity squared over the radius. So for this one, I'm going to say that the radius of my loop is 30 meters. It's a pretty big loop for a car to go around. So in this case, I'm going to substitute some stuff in. It didn't actually tell me the mass of my car, but that also doesn't matter. These masses cancel out completely, and I can just cross them out. They both cancel. It doesn't matter how much my car weighs as far as how fast it needs to be going, because on both sides of the equation we have that mass in effect. So I'm going to rework these a little bit. G times the radius, which I said was 30, and G is 10. So I'm just going to make that 300 total. G times R is 300, and that equals V squared. So our velocity, our minimum velocity to go around this loop is the square root of 300 meters per second, and that is at the top of the loop. At other points we need to be going different speeds, but at the top of the loop, which is going to be the fastest we have to go, we have to be going at least the square root of 300 meters per second, which is somewhere around, let's see, somewhere around 17-ish. A little over 17 meters per second, which really isn't that fast. That's not too bad. But if we didn't have any variables in there, we could just get sort of a generic equation, and the minimum velocity we would have to be going is the square root of the gravitational pull times the radius. So again, mass does not matter at all. This time friction doesn't matter, because friction is not one of our centripetal forces. It's actually pulling back or sort of into or out of the page, sort of keeping our car going straight around the circle. But it's not a centripetal force. The only ones here are the normal force and the weight. So mu sub s has no effect. And this is our minimum speed instead of being our max. So this is the minimum speed we need to be moving to get around the circle without losing our circular motion. We can go faster. We can go really as fast as we want until sort of our body or the car brakes. But we have to at least go at this speed here. And at this point, we're really all the way through everything from the centripetal motion. Again, it's a lot of the same stuff as we had in the Newton's laws unit, the last unit, Unit 2. But this time we're just making a couple little changes to it, where we're worried about forces going into the center of a circle, and we change that acceleration to be m equals v squared over r. So just a couple things to remember. The force and the acceleration, the net force and the acceleration, both have to point towards the middle of the circle. The acceleration is mv squared over r. And if you want, try to remember some of those little equations about the speed, but not having them memorized should not be a big deal. You should be able to sort of derive them. We did that in the notes a little bit. So maybe go over those and understand how we got from net force equals mv squared over r to each one of those variables, how we set those, or I'm sorry, not variables, equations, how we set those up. I think that would be more valuable than just memorizing them. So moving right along into Newton's universal law of gravitation, I won't bore you anymore with sort of the details of how Newton derived that equation, but it is F equals capital G, mass 1, mass 2, over r squared. And that squared is the biggest, it is the most missed piece about this whole equation. It's not a hard equation. A lot of times we're just sort of popping in numbers into it. But forgetting about the square, forgetting that this is an inverse square law, is the biggest, most missed piece of this. Just remember that this is the force of gravity. It is not necessarily the net force, but it is the same as weight. This is weight. It is the exact same thing. So just like we did the mass times that lowercase g of an object that's being accelerated towards the ground on some planet, this is the same exact thing. We're just going at it a different way, slightly different. And let me just make sure I don't have anything. That large uppercase G is the universal gravitational constant. It is 6.67 times 10 to the negative 11th. It's got crazy units. Newton meter squared per kilogram squared. No, you do not need to memorize that. It's on your green sheet, so don't waste your time. Those two masses have to be in kilograms, and this, the biggest point here, is that this is the distance between the centers of mass. So a lot of times with this equation we talk about planets and maybe something on a planet. It's important to remember that that radius is, or that r, that distance, is the distance between the centers of those two objects, the centers of mass. It's not, surface to surface. It's not just what's the distance between them like we think of, the distance between me and the Earth is 0. Well, yes, I'm standing on it, but the distance between my center of mass and the Earth's center of mass is much larger. It's about 6,380,000 meters, I think is the right number. Not entirely sure, but that does not matter. So moving right along with this, we could do some sort of plug-in and chug-in with this, but I have confidence in your ability to plug numbers into an equation. But just a couple little notes to go along with this. Remember, when we're finding this force of gravity, that applies to both of the objects, both mass 1 and mass 2. Second thing is that force is always attractive. Whatever direction it's pointing is always pointing towards the other object. Gravity is never repulsive. It is always attractive. First thing I really want to do with this is also take a look at how we can get the acceleration due to gravity, that lowercase g, from this equation. So we're going to do a couple things. Force or net force is equal to ma, and we've also got the force of gravity is big G m1 m2 over r squared. So if we assume that this gravitational force is the only force acting on our object, we can plug this Fg into our net force equation as our net force. So what we can end up with is G, mass of some object on a planet, the mass of the planet over r squared, and that is equal to ma, or the mass of the object, times a, which is really the acceleration due to gravity. So I'll substitute in a g for that as well. That g could be different on different planets, but it's gravitational acceleration there. From here, we can cross out the masses of the object. It doesn't matter how much the object weighs. It accelerates at the same rate. We've seen that before, just because two objects have different masses. For instance, back in our projectile unit, we still use the same gravitational acceleration for both of them. That's assuming that the objects weigh significantly less than the planet does, which it will be the case for any problem that we do. So really our acceleration due to gravity is big G times the mass of the planet over r squared. Working with variables is a lot more relevant for these types of problems than actually plugging in numbers for them. You do have to be able to plug in the numbers, but multiple choice questions love to just ask you about the ratio between the two, sort of setups. So let's say that we had two planets, and we'll call them mass 1 and mass 2 over here, and they are separated by some distance r. Remember that radius is between, or that distance is between the centers of mass. And let's say that a couple things happen, sort of without reason, but they happen anyway. The first planet triples in mass. So it is now 3 times m1, and m2 doubles in mass to m2, but the radius, I know this isn't to scale, is going to be a fourth of what it was before. They moved closer together. And what we want to know is, what is the difference in gravitational force between the objects here compared to here? And you can sort of do it in your head if you're good at that, but for me that was always a little bit trickier. So we can do it a different way instead. If we're looking at that force equals gravitational constant times mass 1 times mass 2 over r squared, we can sort of substitute in the factors by which each of these change. So the G, the capital G, the universal gravitational constant, did not change at all. It is still exactly the same, so I'm going to call it 1. From start to finish, we multiplied it by 1. It stayed the same. Mass 1 got multiplied by 3. It is 3 times as big now. And mass 2 got multiplied by 2. It doubled. On the bottom, our radius is now a fourth, but that needs to be squared. So what we've got is 6 over 1/16, which is the same as 6 times 16, which is going to be 96, I believe. Yeah, 96. So the force of gravity between these two planets is 96 times greater than it was in the first setup. So let's say that at the beginning it had a gravitational force of 50 newtons. After these two work out and get to this setup, it would have a gravitational force of, let's see, 48,000. Yeah, 48,000 newtons. And we can do this for any combination of changes to the mass or to the radius. I encourage you to do it this way and set it up that way to keep everything straight. When there's a lot of different variables changing, it can get a little bit tricky. The other way we can approach this is with that gravity equals the mass of the planet times the big G over r squared. So a problem might say Bob is standing on a planet that has some acceleration due to gravity g. And Bob then goes to a new planet that is 2 times the mass and let's say it's half as large. The planet is half as large, so he is half as far out, so his radius is 1/2 times r. What we want to know is, what is the new gravitational acceleration on Bob? That's the name of my stick figure today. So we can do all of this the exact same way as we did before. The G is, or lowercase g is capital G, which didn't change. The mass of the planet is 2 times as big, and the radius is 1/2, and again, that gets squared. Let me just make sure I squared that, yeah. So then I've got 2 over 1/4, which is the same as 8. So if the original planet that Bob was on had a gravitational acceleration of, say, 10, let's say he was on Earth, 10 meters per second squared, his new gravitational acceleration would be 80 meters per second squared, which means that he is 8 times heavier on this new planet, which would be very unfortunate for him. He wouldn't be able to move very well, I would imagine. So getting some practice with those two sort of approaches, whether it's between multiple objects or with the acceleration on a planet. And even if you can't remember the equation for g equals m1 with g, the mass of the planet, over the r squared, you can approach this problem the exact same way with the same formula as the last one. Just remember that Bob's mass, or your object's mass, does not change when he moves to the next planet. So it would just be an extra 1 here, which doesn't really change your variables at all, which is nice. The last problem I want to do on this video sort of ties both of these concepts together, and that is using that gravitational force as a centripetal force. Let's say that we've got a planet, maybe Earth, and let's move Earth over here, and we have the moon. Let's get a nice little moon out here. And the moon is orbiting the Earth. Let's not have white. Let's get it so we can see it. And let's just pretend for a minute that that is a nice perfect circle. So it is moving in uniform circular motion. And we're going to say that the moon, and I don't know the real number, I'm just going to make something up here. Let's say that it is 3.4 times 10 to the 9th meters away. That's probably way too small, but I don't have the number here, so it really doesn't matter. It could be a satellite. It could be a moon on a different planet for all I care. It's just some numbers for us to work with. So it is 3.4 times 10 to the 9th meters away from the surface of the planet. And let's say that the mass of my planet is, let's just call it 4 million kilograms. It's a smaller planet. It's probably not Earth. So we've got some moon orbiting around the Earth, and I want to know what its velocity has to be. At each different sort of radius, a different velocity has to be true for an object to stay in orbit, in gravitational orbit. So for this particular distance, I want to know how fast exactly my moon has to be traveling, what its velocity is going to be. So you might be saying, well, Mr. Rombach, if we're going to use one of these equations, we need the mass of the planet. And I'm actually going to show you that is not the case. So I'm going to move some of this stuff upwards so I have some more room to work. So we said that this is centripetal motion, so I know that my net force is going to be equal to mv squared over r, and the m here is going to be the mass of my object, whatever object is orbiting, which is the mass of the planet. So you're probably getting even more and more nervous about this, the fact that we don't have that number, but just hang tight. So the only force that is acting on this orb, on this moon, is the force of gravity that's pulling it towards the center of that other planet, which means that our net force is the force of gravity. Our net force is F sub g. And we know that the force of gravity is big G m1 m2 over r squared. So from here I'm going to shift these up even a little bit further and substitute some more of this in. So now this F, which is really F sub g, the force of gravity, this whole bit is going to get substituted in there. So now I've got capital G mass of my object, mass of my planet, over r squared, equaling the mass of my object, v squared over r. So here's where those masses of the objects actually cancel out. It doesn't matter how heavy my orbiting object is, whether it's a moon, whether it's a satellite, none of that matters. The only thing that matters is how far away is it from the center of the planet, how big the planet is, what the planet's mass is, and the gravitational constant. So we can start filling in some more variables. One of these squares is actually going to cancel out with this radius, so we are just left with the radius there, and we get the square root of capital G, mass of the planet, over the radius, and this is all square rooted together. So G, and that is equal to V. So G is 6.67 times 10 to the negative 11th. And the mass of the planet, I said, was 4 million, hopefully. Yeah, 4 million kilograms. So that's 4 times 10 to the 6th. And my radius, I actually don't know. I told you the sort of distance away from the surface of the planet, but remember we have to measure from the surface to the, I'm sorry, not from the surface, we have to measure from the center of mass to center of mass. So I'm going to say that this is actually going to be 3.4 times 10 to the 25th. It's a small-ish planet. So 3.4 times 10 to the 25th is my actual radius. Be careful with that. There will be test questions, whether it's on the AP test or your actual test, which will give you the radius at, or sort of the altitude that the object is orbiting at, as well as the radius of the planet, and you're going to be expected to know to add those together to get the entire radius that you use in your equation. So I said that was 3.4 times 10 to the 24th was my total distance, the radius plus the altitude, and all of that has to be square rooted. So let me get that square root in there. So I just substituted in all those values, and that is equal to my velocity of the orbiting object. And if all my math came out right, that should be a velocity of 8.86 times 10 to the negative 15th meters per second, which is very, very slow. But you have to realize that this object is very, very far out from the center of that planet. The gravity is not affecting it that much. It is pretty far out there, probably way too far to be even close to reasonable. But if you did those calculations right, then you are in good shape. Yeah, that's actually really far. Absurdly far, in fact. So, but if you wanted to orbit at that speed, then go for it. So this is pretty much all I've got for you as far as this video. I hope it was beneficial for those of you who chose to watch it. Enjoy studying, and hope you are prepared for the test. See ya.